Hello. In this recording, we're going to learn about exponential and logarithmic functions that are not base e. So the previous two lectures that we've had, we've looked at the natural logarithm and the natural exponential functions. We've learned how to differentiate these and we've learned how to integrate these. But there are other bases to consider. And by base, I mean, well, let's look at this definition first. So let a be greater than 0 with a not equal to 1. That will be our base. And let x be any real number. Then the exponential function with base a is denoted by a to the power x. And this is defined by this equation here in terms of the number e. So a to the power x is equal to e raised to the power of natural log of a times x. That's how it is defined in this textbook. So what we've been studying is just simply e to the power x, right? Which you would see matches up here. E to the power x is equal to e to the power of natural log of e, which is just 1 times x, so it matches up. But other bases occur often. For example, 2. Base 2 happens quite a bit in exponential growth. So we need to at least learn how to differentiate these types of exponential functions with other bases. And that will be the main goal of today's lecture, actually, is to learn to differentiate exponential functions with different bases. For integration, we can put that off and just, when we get there, I'll show you that you can just convert it to the natural exponential when you do that. Okay, so what's the second part of this definition? The logarithmic function with base a, denoted by log base a of x, is defined by this equation here. So log base a of x is equal to 1 over natural log of a times natural log of x here. Okay. So you can see that when we have base e, we have log base e of x, which is ln of x, is equal to 1 over natural log of e, which is just 1 times natural log of x. So you see that it works out there as well. Now, as before, the natural log and the natural exponential functions were inverses of each other. These are inverses of each other as well. So, so if I say like f of x equals to a to the power x and g of x equals to log base a of x, these two functions are inverses of each other. And again, provided a is greater than 0 and not equal to 1. So because these are inverses of each other, they're going to satisfy all the properties of being inverses. So for example, I can write down, so inverse function properties. And these are properties that, again, like you've probably seen in like a college algebra course or a pre-cal course. We're just kind of restating them again. So one, which should the first one be? The equivalence relation between exponentials and logs, where you can transfer them back and forth. So you can say y is equal to a to the power x if and only if, so this is an equivalence, x is equal to log base a of y. I don't know if you can remember your college algebra course, it might have been a while for you, but this is equivalent to this is equivalent to that. Okay, you can go from one to the other. If you have an exponential, you can always write it as a logarithm. If you have a logarithm, you can always write it as a exponential. 2. So the second one should probably be O. So if we look at A log base a of x, this is just going to be equal to x. And that's provided x is greater than 0. And again, this is just standard properties that you might have seen before. Also, if we have log base a, so log base a of a to the power x using the exponent rule, this is just going to be x. And this is for all x. Okay. Now again, all the normal properties of logarithms hold still. In particular, the addition rule, the subtraction rule that we were using with the natural logarithms, and also hold with these log base a logarithms. So for example, just like remember, so this is not a part of the inverse properties, this is just like properties of logarithms in general, that like for example, if you have like log base a of x plus log base a of y, and that's going to be log base a of x times y. Right? And similarly, if you have log base a of x minus log base a of y, this is log base a of x over y, and divided y is not equal to 0. That's the other one. Log base a of x to the power n is equal to n times log base a of x. Like all of the standard rules still apply there. I'm almost tempted to show you how to like argue why one of these might be true. Yeah, I suppose why not? Why not just show maybe like number 1 is true or something? Maybe. Let me take a look. So we can show this just by looking at the properties, right? All of these rules are, you can derive them, right? These are not, they don't just come out of nowhere, right? We should be able to at least like show one of them by using that rule. So maybe let's kind of think about why one might be true, or why this one might be true. So what do we want? We want to show that log base a of x plus log base a of y is equal to log base a of x times y. That's what we want to show. So like we're trying to justify like why this is true to ourselves. Like suppose we were being inquisitive about this and you weren't just like taking my word for it, right? And you have this, and this is just a property of being an inverse. This is literally a definition of the inverse function. And because these are inverses, they must satisfy this. So, what can I say? Okay, so I'm going to use this definition here. Okay, so if I say the x's and the y's might be throwing me off a little bit. What if I did this? Thank you. Make P and Q. P times Q. P, Q. P divided by Q. That way there's no mix up between the x's and the y's of different. And these are the properties. There's like P right here. And we're trying to show this one. So we have a rule here, right? So let's say that suppose log base a, and we'll replace this by P and Q. just so we don't get confused with the other notation. Hopefully you can still see that. PQ, okay. So suppose log base A of P is equal to X1. And log base A of Q is equal to X2. Okay, so then this is X1 and that's X2. So then we want to look at this sum somehow. We have to get there. Now we're trying to show this equation is true. We have this and we have this. All we really have to use is the definition of the inverse. So that's true if and only if that's true. So we have our P here, which is like the Y. So then P is equal to A to the power X1 from there. And Q is equal to A to the power X2. And eventually, right, I want to get to P times Q. So if I have this, which is that, and I have that, which is that, I can convert them to these two equalities by just using the definition. And then I can multiply P and Q and see what happens. We have maybe P times Q is equal to that times that, right? Oh, but these have the same base. And whenever you have the same base and you multiply, you just add their exponents. So this is going to be equal to A to the power X1 plus X2. So what do we have? We have that P times Q is equal to A to the power X1 plus X2. That's an exponential equation. We can take that exponential and now we can write it as a logarithm. So PQ is equal to base A to the power that, if and only if the power is equal to log A of that. Oh, but what's X1 and X2? X1 is equal to log base A of P, X2 is equal to log base A of Q. So then we have log base A of P, which is X1, plus log base A of Q, which is X2, is equal to this side, log base A of P times Q. All right, so that's a rough sketch of why part one would be true. The mathematician in me wanted to just verify that for you. You wouldn't be asked to verify this on your own, but I'd like to think that you're inquisitive enough to try to make sure these equations that I write on the board are true, right? Now, a similar type of argument, you can show that, and a similar type of argument, you can show part 3. Just by using this definition. Okay, so now I'm going to pause the video so I can erase and then write down the rules for differentiating, for taking the derivative of exponentials with base other than the natural base. Okay, so one moment. Okay, so here is the main theorem of this section. So this theorem is concerned with taking the derivative of any logarithm or exponential with a base different than the natural base, and it covers all the cases that you'll ever see. Okay, so let A be a positive real number that's not equal to 1, and let u be a differentiable function of x. Under these assumptions, these are the formulas for taking the derivative. So, oh, I almost forgot one here. This is natural log of a times a to the power x. Okay, so the derivative of exponential function a to the power x is natural log of a times a to the power x. And you can derive this based off of how we defined this function. Okay. In particular, it was what? It was e raised to the power of natural log of a times x, right? What's that derivative? It's that. Same thing. And I encourage you to go back and verify that. And then once you have that, then the chain rule gives you part 2 here. The derivative with respect to x of a to the power u is just natural log of a times a to the power u times the derivative of the inside, du dx. That's the chain rule. Okay. In a similar fashion, you get 3 just from the definition of log base a of x. Right? This was defined in terms of the natural log, so you just take the derivative of that definition, and this pops right out. And then once you have this, if the inside was a differentiable function of u, you multiply it by du dx, chain rule. Okay. So let's quickly go over like a few examples. The first one will probably be easy. Yes, very easy. So maybe let's write find the derivative. Okay. So let's look at like y is equal to base 2 to the power 3x. Okay, now this should be fairly simple to do. There's your function of u, 3x. I mean, function of x, 3x, that's your u. There's your base. So we're in this case right here. So it's really simple. So y prime is going to be natural log of 2 times 2 to the power of 3x times 3. Du dx is just 3. A cleaner way to write this would be move the 3 over here, and then you can bring it up as a power. So you really could write this. Hopefully you can see how to get the noted there. 3 times natural log of 2, bring the exponent up, 2 to the power of 3 is 8. So natural log of 8 times 2 times 2 to the power of 3x. Okay, what about b? Y is equal to log base 10 of cosine of x. Looks a little bit more complicated, right? But again, this is like your u, your base is 10, you just use the formula. So y prime is going to be equal to 1 over natural log of 10. Make sure, yeah. 1 over natural log of 10 okay, times x times du dx. So in this case here, that'll be negative sine of x. No, I knew something was off there. That's u. So this should be cosine of x. Yep. 1 over natural log of a times u, because I can see like if you derived this from this, necessarily there'd be a u there. All right, so let's look at one more. C, they say y is equal to log base 3 of root x all over x plus 5. Okay. Now, a lot of you made things so hard on yourselves with the first exam by applying some rule without simplifying what you're looking at first. And I'll explain that more once I get everyone's exams in, because people still haven't turned it in for some reason. So for example, here, I'm going to expand this out before I start differentiating anything. I don't want to differentiate that over that. If I can expand it, I will. So if I do that, I get that this is going to be equal to log base 3 of x to the power 1/2 minus log base 3 of x plus 5. Right, this is division, I can always expand out. So then I can simplify even more by bringing that exponent out. I can't do anything here. So now each piece is relatively simple, and I can just apply those rules over there. So this is going to be y prime is equal to 1/2 the derivative of that, which is just 1 over natural log of 3 times x minus 1 over natural log of 3 times x plus 5, that's u, times du dx, which is just 1, so here. Okay. Now, you will encounter these sometimes as a data scientist, and because of that, I'm going to assign some suggested problems from this section. So 5.5 homework suggested problems, which you really should do them, especially for the next exam. 39 through 59. Okay. You don't have to turn them in, but you want to do them for practice before the next exam. Okay? That'll be it for this video.